What is the first thing that comes to your mind when you hear the words quantum computing? For a lot of people, particularly those who have no prior experience in the field, the word quantum brings up the image of a mystical, complex, and daunting subject. The goal of this course is to demystify some of the misconceptions that might surround this subject. Having said that, I will not say that quantum computing is an easy subject, but I will point out that what makes it challenging to a lot of people is the fact that it is unintuitive and abstract. Our goal in this course is to provide you, the learner, with a solid foundation of the basics of quantum computing. The reason quantum mechanics is unintuitive is because the world that we see around us is macroscopic. We do not see quantum phenomena as part of our everyday experience. Compare that to a subject like classical mechanics. We get to see these phenomena in everyday life. If we throw a ball at a wall, we see that it bounces back off the wall. So we are easily able to grasp one of Newton's laws that says every force has an equal and opposite reaction. On the other hand, we are not used to seeing balls magically go through the wall and come out the other side. So when we have a concept in quantum mechanics that says an electron can tunnel and cross a barrier and go to the other side, we find it hard to visualize. Having said that, just like there is an equation that describes the ball bouncing off the wall, we have a precise equation that describes an electron tunneling through an energy barrier. So because of these reasons, quantum mechanics can at times seem like a mathematical, abstract and unintuitive subject. But in fact, a lot of the mathematics involved in quantum computing is just advanced linear algebra with a bit of vector calculus thrown in. The only prerequisites for this course are high school physics and a familiarity with the basics of linear algebra. If you are not in touch with linear algebra, you do not have to worry because that is where we will start our course. The course is divided into 5 main sections. The first will deal with the fundamentals of linear algebra. It is designed to be a sort of refresher for the concepts that we will need later on in the course. We will then move on to quantum mechanics, where we will again start with the absolute basics. Starting with the concept of how an electron can be described as a particle and as a wave. We will see that we no longer have certainty in the position of an electron. We only speak of the probability of an electron being at a particular place or in a particular location. We will see how we can use the various possible states that an electron can be in. In fact, it is these various states that an electron can be in that we use for calculations, or what we call as quantum computing. We will explore these details in the second part of the course. Now you know that for classical computing we use bits which can take on values of 0 or 1. Similarly, for quantum computing we have quantum bits or qubits which can take on a range of values or a linear superposition of values between 0 and 1. We know how bits 0 and 1 are implemented in the electronics that we use. We will see how qubits are implemented. There are some broad ways in which qubits can be implemented. You can have superconducting qubits, electron spin qubits, ion traps, diamond vacancies, optical qubits, and so on. We will take a look at the advantages and disadvantages of each of these implementations. If you are someone who is interested only in the software or algorithm side of quantum computing, then you may not really need this information, but it does help to know some of the basics so that you have an idea of what is possible or not possible to build in hardware. In the third part of the course, we will see that just like we have logic gates in classical computing, we have logic gates in quantum computing. We will look at how quantum logic gates are built. Just like we have AND, OR, NOT and XOR operations in classical computing, we'll see the operations that we can perform with the quantum bits. There are some operations like the NOT gate that are similar to the one in classical computing, and there are some gates that are quite different from those that we see in classical computing. One problem with quantum computing is that we currently do not have the ability to control qubits as reliably as we are able to control bits. In classical computing, if we have a 0 or a 1, we are quite good at keeping it at a 0 or a 1. Quantum bits, on the other hand, are much more fragile and vulnerable to external noise. We will look at what quantum noise is, and because qubits are so fragile, we need error correction codes to be able to do meaningful computations with qubits. That brings us to the fourth part of the course, that is quantum information, where we will specifically look at quantum noise and quantum error correction codes that are used to deal with this. Finally, in the fifth and final part, we would like to give you some hands-on experience as well. So we'll be designing some lab exercises and assignments where you can apply the knowledge that you have gained and test your understanding. Overall, in this course, it is our goal to give you a foundation and the basic tools using which you will be able to learn more advanced concepts and hopefully build a career in quantum computing.